are you able to share the screen?
Yeah. Can you see my screen?
So it's not in the presenter mode, but we can see the PowerPoint.
You should be able to see the PowerPoint, right? So now it's make the full screen.
Yeah.
It's okay?
Yep. Okay, so yeah, hi everyone, and welcome to another week of the ML Lunch Series here at Vanderbilt. Today, we're lucky to have Dr. Lingfei Wu, who's a principal scientist at JD.com, the Silicon Valley Research Center. Previously with IBM TJ Watson, has received numerous awards, both in industry, including multiple Best Paper Awards, has had his work extensively covered in the news. And today he's going to talk about quite a diverse topic of the graph neural networks, the foundations, frontiers, and applications. So thanks again.
Thank you very much, Tyler, for your very nice introduction. So first of all, I would like to thank all my collaborators, Professor Peng Cui from the Tsinghua University and Professor Jian Pei from the Simon Fraser University and Professor Liang Zhao from the Emory University. So without them, this work cannot be done. So as you can show here, that so today I'm mainly talking about basically a book. So our recent Graphene Units book that being published by Springer in earlier this year. So the outline here is well aligned with our book organization. So we'll talk about three different parts. So first part, I'll talk about the foundations of the Graphene Units. So here we will talk about why we care about the graph and what's a brief history of the Graphene Units. And we will also introduce deeply introduce the one chapter content about the basic algorithm and the method in Graphene Units. And we will quickly go through our foundations topic in this area as well. And then in the second part, we'll talk about the Graphene Units frontiers. So we will talk about, kind of a showcase two research chapter. One is the graph matching, and the other one is graph structure learning. And then we will also quickly go through other research frontier topic in Graphene Units. And finally, so we will showcase a recommendation system. So how today's recommendation can leverage the power of the Graphene Units. And we will also talk about a few other applications with Graphene Units as well. So as can show in the right-hand side, this is the website. You can see all the pre-publication electronic copy in our website, and also a few other links for the book. So the first part, so why we care about graph, right? So I don't know how many people take Tyler's courses. I think probably majority of you already have some foundation about Graphene Units. So I will quickly go through each part. So regarding what is graph, right? So as you can see that graph is actually a language for describing or modeling a very complex system. So but graph structure itself is quite simple, right? It's just a bunch of the graph nodes that can denote some object. And then you have an edge to describing the relationship between any of the pairs of the graph node. Just I'm showing you this real example, right? So in modern, any modern system, whatever is a social network or is a search system or is a recommendation system. So basically, we are as a human being interaction with all the system, and you actually have been included in many different kind of networks, right? So like in JD.com, so you are a customer, you purchase the item in JD.com website, and essentially when you send the query to the system, we will based on your user profiling information to return most matched result based on your query or recommendation or based on your history transaction behavior. So when we talk about the deep learning on graph today or Graphene Units, so we essentially means that this type of the method will take a graph topology and graph node sign and well as sign information as an input. When we talk about sign information, it could be a node attribute, it could be edge attribute, but also have like node type and a type stuff. So as you can see that, so graph structure data is really everywhere, right? So ranging from the internet to social network, from the information retrieval, recently also like in biomedical, in the like drug discovery area is a very hot topic today. So people try to model the chemical compound as a biomedical graph and try to find new drugs. And also, for the program and graphs, people use this Graphene Units to do, to leverage on the graph that, for example, control flow graph or data flow graph to do the variance of the graph analysis. Even in the computer vision domain, people have been using Graphene Units for various kind of visual reasoning. So this is a very interesting plot that showing that how graph machine learning is really a very hot topic today. So the number of the paper that's associated with graph is really increased exponentially. So one critical milestone is really a beginning of the machine learning on graph is this in 2016. So let's go to our next slide to talk about a brief history about Graphene Units. So in the today we have seen so many papers in Graphene Units, right? So this is one of the most hottest topic in machine learning community and also data mining community, and as well as a community as well to leverage the power of the Graphene Units. But really the first paper published in this domain is go back to the 2009. So that is even before the rising of the deep learning, right? That's in 2012. So this is very interesting. So and later in really the modern Graphene Units is first time have been proposed in the 2016 by Ijali from the DeepMind. So we call the graph getting network. So this is basically the kind of the modern version of the paper to improve the scattering Graphene Units that is proposed in 2009. And because of that, so later people also proposed GCN graph convolutional network. That is really a first paper that's starting a new era of the graph units, because this paper is showing that so how we can do a very simple operation using graph units, and then you can achieve a very promising result. So between the 2017 and 2021, we see that people have been starting a serious graphical, serious work that from the different perspective, for example, graph convolution, message parsing, attention-based method, and even unsupervised graph units. And then, we can see that today many more graph units have been fastly developed every year. So starting from the 2019, 2021, we see that so because the Graphene Units method become a mature and mature, so people are starting to develop a various of the applications that is try to leverage the power of the Graphene Units, right? So for example, in the searching system, in the recommendation system, drug discovery, NLP, intelligent transport, and we also see that so there are a lot of the open source library being developed surrounding the Graphene Units. For example, the most of two famous one is Deep Graph Learning library developed by the Columbia, Shanghai, and AWS, and also the PyTorch geometric is other one that's very popular in the research community, because it's very easy to use. And we also see that a lot of dedicated libraries that have been rising in the last 2 years. For example, we have developed this called the Graphical NLP. Essentially, try to make the using the Graphene Units it's very easy for the NLP community. And also, this touch drug is really to develop, try to leverage the power of the Graphene Units for the drug discovery. So we also see that many new books have been recently released and published. For example, there are 3 new books published in 2021. One is from the Professor Liu from Tsinghua University. This is a very early book. Yeah, this book is very it's short, but it's early attempt to try to summarize the variance of the Graphene Units method into one book. And Professor Tang, Jiliang Tang from MSU, wrote this book, Deep Learning on Graph. So this is also TEDx PhD advisor. So this is a great book that have been trying to summarize all the state-of-art method have been developed surrounding the Tang's group. And Professor Hamilton, very usually student, so as now he's not a professor, he now go to the Citadel. So I wrote this book, the Graph Repetition Learning book. This is a very nice book. I really enjoy reading this book. So early this year, so we have been published, currently I think it's the most comprehensive Graphene Unit book called Graphene Units, Foundations, Frontiers, and Application. So in this book, I have been including around 27 chapters, try to discuss the Graphene Units in various of the topics, foundations, frontiers, and applications. And so this is kind of our attempt, try to bridge a gap between this fast and growing area, and also many people still are not aware of this research area. Try to have kind of like one kind of like wiki type of the book to showcase all different topics so that people can quickly grasp the big picture about the Graphene Units. So, but as you can see here, right? So the machine learning on graph is not a new topic. Okay, it's been there for at least 2 decades. So classically, so we can see that there are many machine learning tasks already on graphs. For example, the classification task that try to, once you have a linear representation with a graph node, you can predict a given type of the graph to predict the node type by giving node. And also we can do the link prediction, try to predict so if 2 nodes are linked or are related. And community detection means that so you try to identify a bunch of the graph nodes, are they behavior similarly or not? And graph similarity means that so you try to compute the similarity between 2 graphs or subgraphs so that you can use for some applications. But with the rising of the deep learning, so today we are more focused on the Graphene Units type of the method. And one of the most beyond the variance of the method that the people have been presented in over the last few years regarding Graphene Units. So right now people want to know more and deeply understanding about so how is the expressive power of Graphene Units is. And but in order to leverage the Graphene Units in the real applications, the scalability becomes very important topic. So therefore, another fundamental topic is how to scale up the Graphene Units so that we can deal with the graph that is billion size. And so in other applications, especially for some life critical or some search recommendation system, it's also important to understand why you make this decision. Okay, so in that sense, so interoperability becomes very important topic. You want to develop a model that is interoperable so that later you can use the information to gain more insight about why you make this decision. So last one, I think is also a very important fundamental topic in the sense that so we all know that the neural network is very sensitive to the adversarial examples. So same issues or phenomenon also happen to Graphene Units. So how to develop an effective adversarial attack and the probable robustness algorithm to defend this attack on this very important topic for any kind of real system. So so this part, so I will briefly introduce the Graphene Unit for node classification. So basically this is content that's introduced in the chapter 4. As we all know that so feature learning is a very most important part for the machine learning cycle. So with the rise of the deep learning, people tend to automatically learn a feature for a neural net. And so this is essentially trying to transform the original raw data to its structured data, or you can call it the feature matrix, right? And then it's fit to the learning algorithm, you learn the model. So same thing for the graph, graph representation learning. That our goal try to design an efficient task independent or dependent feature learning algorithm so that we can learn a very impressive graph representation representation. So I can see here that so essentially our goal is try to define a function that can transform the original graph node into its embedding space so that we can use a density vector to represent the original graph node, such as that so the original possibility and all this original topology information and semantic information can be preserved in the original space. So in Graphene Units, so one of the most important foundations is the process of the learning node embedding, which try to define graph filter and apply on the adjacent matrix and initial node attributes. and then try to update the node embedding to learn a better representation, and then use that for any downstream task. It really depends on the type of the graphic filtering operation. You can roughly categorize them into the 4 different categories: spatial-based method, spatial-based method, attention-based method, and a recurrent-based method. However, the graph filtering operation don't really change the graph structure. So if you want to learn a graph level embedding, you have to design a different operation. So the pooling operation is one type of operation try to solve this problem, that will take the input graph and the input node embedding, and then to generate a smaller graph with a few nodes and with corresponding new node embedding. So roughly speaking, we can cover them into 2 different type of category. One is a flat graph pooling. So this is a very common use in many applications, okay, especially in the NLP domain. So you basically just use a very simple pooling operation, for example, max pooling, average pooling, or bin pooling, and most of the time it's already enough. And however, in some of the dedicated domain, right, if you want to do the graph classification, it's important to design more certificate algorithm to do the better graph representation learning for a whole graph. So in essence, like a hierarchical graph pooling type of method through the coupling operation become a very important type research topic, where they try to learn a graph representation in each of the layer, and then to put them together, to fuse them together, and to generate the final graph level representation to summarize the whole graph. So this is basically a basic model regarding Graphene Units. So I'll go very quickly this part, because I know that most of you must be already learned a lot from the Titus courses. So the key idea here essentially, is try to generate a node embedding based on the local neighborhood. So given that you have a target node A, so if you want to learn a representation for A, it will have to learn the context information, which typically can be defined as a neighborhood, right? So BCD is the first order neighborhood, and this neighborhood will be most important context information to define the representation of the A, and therefore that you can uniquely define a computational graph for each of the graph node. And so once you define the unique computational graph for each graph node, you can design a neural nets, right, to do the neighborhood aggregation and to generate the representation for each of the graph node. So in the first layer is always its initial attribute, and this is been showing a very important factor to the final performance. And this is definitely reasonable, right? Because you want to take advantage of the physical milling of each graph node, so that you can leverage this type of information for the model training. And conceptually, the model could be arbitrary depths, right? Because you can have many layers, but in reality, you are not, right? So for example, different type of the Graphene Units, they will have a different kind of depths. And if you have a design very deep Graphene Units, you will often have this overfitting problem. And this is also one of the active research area as well. So this is basically define an overview of the Graphene Units model. You can define a neighborhood aggregation function, and then you can aggregate the information from first layer, and then propagate that message to the second layer, and then your second layer you can aggregate the information again, and then to propagate. So then finally you will generate a representation for each of the graph node, and then you can define a loss function based on this embedding have been learned. And when you train this Graphene Units, you basically train on set of the node, which can be defined a batch of the computational graph. And then you can generate an embedding for each node as needed. So one of the interesting about this type of the learning paradigm is that even the node may not be seen in the training phase. In the testing phase, you have some new node coming, and you can still generate an embedding for that, because you are not learning a parameter for each of the graph node. Instead, you are learning a aggregation function. Okay, so now let's take a very simple function as example. For example, if we here the aggregation function can define as an average message, right? So this is probably the simplest operation. You just use average function to average a message from each of the neighborhood, and then you can apply a neural network to generate the final one. And this is kind of like a basic math behind the message passing process that we have been talking about in the previous several slides. And then in the first layer, right, you have this layer 0 embedding, essentially can be treated as an initial node attribute. And then you can try to transform that into the latent space, and you average the labels previous layers embedding. And then to generate what we call the message, and then we can fuse this message with the graph node embedding from the previous layer, and then to go through a nonlinear transformation layer, and then to generate a new node embedding from current layer. So basically, we can see that. When we try to generate node embedding, it's a kind of a simple idea, right? So you try to generate node embedding by aggregating the neighborhood information. So if we treat this kind of as a messing passing perspective, and the good thing about that is allowing for the parameter sharing and encoder and allowing for the inductive learning. So this is just a very basic model trying to illustrate how Graphene Units works, right? So in reality, it's really depends on how we design the graph filter operation. So for example, as we briefly mentioned before, right? So the spectrum-based graph filtering is a very early stage. So develop the method. So two representative methods like GCN and chip-shaped Graphene Units is really try to cast all this stuff as a spectrum operation. We'll discuss each of the type of method in detail in the next few slides. And so also people have been deriving various Graphene Units based on the spectrum-based graph filtering. And the one that we just simply introduced is basically this type of the method. And in this type of method, we have quite a few representative methods in this direction. And also based on the importance of each graph node, people have been also designed is called attention-based graph filtering, try to capture the importance of each graph node so that you can generate a better message depends on the attention score you have been computed. Finally, so for the recurrent-based graph filtering, it's a bit special because when they design that, so it's using to leverage the gating mechanism and also try to generate a sequence of the output. And this one is, even though it's early work, but it's quite a bit special compared to the field's early work. So this is basically the first type of method we want to introduce, the graph convolution network. So this is probably the most cited paper in this domain. So the key idea here is to try to apply a spectrum convolution on graphs. So where the convolution can be defined as a graph filtering operation, a modification between the graph filtering operation and the graph signal. And here we can see that, so basically you try to perform eigen decomposition of the adjacency matrix to compute the eigenvector U and also have a function over the eigenvalues. You can see that if this adjacency matrix is very large and sparse, this eigen decomposition become very expensive. Okay, so therefore the people later try to propose a chip-shift polynomial type method to accelerate the computation. However, it's showing promising result, but not powerful enough. So later in the graph convolution network, this proposed by Thomas. So in 2006, so this is, they have been smartly using this first order approximation, which actually is just a matrix and matrix vector operation. It's make it much easier to compute. And it's also quite fast compared to the existing method. And showing that so that's achieve a very promising result. So this is really a pivotal way to most of people to realize how powerful Graphene Units we can achieve. And later, based on that, people have been doing so many methods and try to find the connection between the graph convolution network and other type of the Graphene Units. So the messing passing is another very popular method. So basically to cast the whole problem from the graph convolution problem as a messing passing process. Okay, so there are two types of representative method. The MPNN essentially is probably the most generic method in this domain, in the sense that so it basically try to define two types of operation. One is aggregation function, other one is update function, and they also treat the node and the edge embedding separately, so that it's a very generic framework. Okay, so so basically the first to aggregate the node and the edge embedding as a message, and then fuse that message with the previous node embedding, and this updating function could be also very flexible. So therefore, that this can be treated a very generic operation. However, according to its original design, so it would be very expensive if the number of the nodes are large. Okay, that means that each graph node are very dense. Okay, so in that sense, people have been trying to overcome that problem. The graph stage is one method that can overcome this problem. So first of all, they simplify this node embedding. This only consider node embedding, but I think edge embedding can also be considered. Okay, but in the paper they only consider node embedding, and also the most interesting part is that they are not trying to aggregate all the node neighborhood. Okay, they just try to do sampling, try to sample the node neighborhood, so that keep to obtain the fixed number of the neighborhood. So there are two merits about that, right? First one is that you can definitely reduce the computation cost, because it will be much smaller if the original graph neighborhood is very dense. The second one is that you can definitely reduce overfitting, because it's not necessarily to consider all the neighborhood in order to aggregate message, right? So you just need to consider most important information. So that part also can help the graph stage can design a quite deep graph units compared to the other one. So the graph attention network essentially is further to design in a different way, in the sense that try to dynamically learn the weights on the edge when performing messaging passing, because all the existing messaging like they assume that all the graph neighborhood nodes contribute equally, but that is not the reality, right? So some of the nodes maybe play more important role compared to other nodes. So therefore, they first learn this attention, and then to do this weighted sum to get to the final node embedding. So this definitely makes sense. And also when they compute this attention score, they basically borrow the idea from the transformer to doing the self-attention, and then to get to the generate the weight. So the last one is gated graphene units. This one is a bit special because all previous methods almost working on the undirected graph. So this one is they are working on the directed graph, and they try to leverage two things. One is that they split the incoming outcoming edge so that they create not adjacent matrix but augmented matrix. Okay, and then they can using a gating mechanism, for example, use a GRU to fusing the node embedding between the previous node embedding and also the aggregated message. So make it suitable for some of the particular applications. For example, if you want to predict a sequence of output. So that's basically kind of like case studies showing that. What type of the graphene units that today people have been developing, and so beyond that, it's also very important to understand how impressive power of each graphene units method. What's the upper bound for that? So they have been in the chapter 5. So we have been talk about the impressive power of the graphene units. Try to improve this impressive power by injecting more inductive biases into the model, so that we can also keep in the model complexity, and also to theoretically understand what's the kind of limit and how to break through this limit for kind of graphene units. And this is a very interesting chapter. Yeah, so I encourage you guys to read that, if you have interest. And so in the chapter 6, we will also talk about scalability. Because scalability is very important in reality, right? So in reality, in the integer application, often you have a graph that is definitely more than million and often go to the billion, right? So in that case, how can we leverage the graph analysis is become very important. So therefore, starting from the 2007, people starting to do all kinds of sampling stuff, right? And along the node wise and the layer wise and the graph wise, you want to develop faster and faster graph analysis, to scaling up the graph units computation. So interoperability is also a very important topic, fundamental topic, because in so many applications, you don't want to only have a result, you also want to know why. So in that sense, it's very important to understand if my original node feature play important role, or if some important node, if some graph node play some important role, or if some very important edge that play important role. So all this information, we want to develop this interpretable graph units to do this job. And for the adversarial rebuttality, it definitely is very important, because in the modern system, you want to make sure the system is robust and is secure, right? So therefore, that is very important to discuss that. So how the adversarial robotics will affect the performance of Graphene Units, and how to design all kinds of the defense mechanism, try to defend all kinds of attack. So this basically finishes the first part. So in the second part, so we will talk about. So in the second part, we will talk about the two Graphene Units research frontiers, and also we will briefly talk about other frontiers as well. So the first part we'll talk about is the graph matching network. So graph matching network is a very interesting one. So for example, right, there are so many applications that you want to do the graph matching. For example, the graph stream matching, searching for the graph-based database, right? And also in the image, for example, you want to do the 3D action recognition. So once you put them, model them as a graph, essentially you're still doing this graph matching stuff. You're giving a query and also try to find the corresponding subgraph that's related with that. And also like unaware malware detection, promise detection, and in the automatic steering probing. So the graph simulated machine learning is defined as the following. Okay, so you have a given a paired graph input, and now you try to compute a similarity score between two of them. They may have two different type of the task. One is classification task, other one is a regression task. So this is kind of like a particular architecture that in this domain, but there's many other methods. Okay, so if you're interested in details about all kind of the graph matching network, you can take a look at chapter. But here we just try to introduce some special one. So here, for example, there's one called the multi-level graph matching network. So or called the hierarchical one. So you can see that here we have two different type of architecture. One is try to take into account the global level of the interaction between two graphs. Of course, that's important, right? Because just as we mentioned, the graph level embedding that is important representation. Try to summarize the whole graph. So use that to compare the graph level representation to capture the global level interaction. It definitely is, will capture many semantic information. But at the same time, that will lose detailed information about the graph itself. Therefore, that is very important to capture other level of interaction. For example, the most effective one operation is a node graph level interaction. This is a cross level interaction. So this is basically the, you can use some of these Graphene Units to try to capture the graph at global level and interaction. And in the node graph level interaction, it's become very interesting. So basically, you can using kind of like a multi-perspective across attention, try to compute the interaction between one of the graph node and also the whole graph, so that you can generate a weighted sum of the graph representation for the new graph representation, so that then you can put them together to generate a new graph level node level representation for each of the graph node, and then you can use that to compute the final representation to generate the final similarity score. And so this kind of like experiment to show you that there are a performance experiment on four different, basically two different tasks, classification tasks and regression tasks on the 4 different data set. And so this is, we can see that, so if we can take into account the global and the cross level interaction, you are able to capture a much better result compared to all the existing state-of-the-art method. So using state-of-the-art method, some of them is captured like global level, some of them capture global level and the node level. But the very few method consider this a node graph level. So this is in the regression task. So the experiment result is consistent with the classification results. So the other one we call the graph structured learning. So the problem is here. So okay, so although the graph units is quite powerful, but essentially it's require the graph structured data available. But in many applications, it may not be true, right? So for example, the intrinsic graph structure maybe is not optimal. Okay, maybe it's noisy. Okay, and also in some other applications, you even don't have graph structure data available yet. Okay, so in that case, so how can you better leverage the power of the graph units to become an important research topic? So here's a basic research formulation, right? So the input is a row graph, and here you assume that this graph is a noise graph, right? So that means that the initial adjacent matrix A0 is noisy. Okay, but the X here we assume that it's not noisy. Okay, that means that the node attribute is clean. But definitely, right? You can extend this setting by considering X is also noisy, and so the goal here is that is not only to generate a node embedding, but also to generate optimize the graph adjacent matrix A, so that you can by learning the graph structure at the same time to learn graph embedding as simultaneously. So this is basically one of the architectures that we recently proposed, so-called iterative deep graph learning. So basically, there are three different components. So once you're giving a data point as an initial graph topology and also adjacent matrix, and also the node attribute, so you can cast a graph learning problem as a similarity matrix learning problem. So therefore, so you can generate a graph topology. But this graph topology definitely is fully dense, right? So just like self-attention, like transformer. So, but in reality, right, it's definitely not good because some of the graph similarity score maybe too small. Okay, that is still noisy. So you want to pruning your learned graph by removing this noisy edge. So therefore, that you can apply graph regularization to control this smoothness, sparsity, and connectivity. And once you have that, so you basically get a refined learned graph topology, and then you can feed that to a graph units, and then to generate a better graph embedding, and then you can iterate, give back to the graph similarity learning component, and to iterate, and finally to automating learning the graph structure and graph embedding, finally to generate a result for both. So this is a little bit details about how to design treat the graph learning as a symmetric matrix learning problem. So design a multi-head weighted cosine similarity, and then you can do this graph sparsity to pruning your learner graph. And most importantly is that the learner graph is important, but the original intrinsic graph is available is also important, right? Because it will carry information, although it's noisy. Therefore, that is better to learn a combination of them. So the lambda will control the contribution of each part, right? So if, for example, if in the intrinsic case, if lambda is 0, it means that the original adjacent matrix cannot be trusted at all, right? So in that case, so we just eliminate this original the power, the effect of the original adjacent matrix. But in other sense, maybe the learner graph, maybe it's play an important role, right? Although it's have a noisy information, and then the learner graph can be seen about the kind of a delta on the initial graph topology. Therefore, that the lambda could be some middle number, right? Like 0.8 or 0.7. That's really one of the hyperparameters that you should tune. So this is basically a little bit details about the graph regularization term. So here we try to adapt the techniques that from the graph learning community, and then try to optimize, treat them as a regularization term to optimize, to controlling the smoothness, connectivity, and sparsity. So this is basically how algorithm. So how can we iteratively to generally learning the adjacent matrix and also the node embedding. So the key idea here is that so you can refine the adjacent matrix with updated node embedding at the same time. So you can also refine the node embedding with the updated adjacent matrix, and therefore they can also let you to learn the both part, and then finally you can stop. When you have been learned optimize the graph structure, but how do you know? So one of the simple way, you can definitely define a maximum number of iteration, right? But this is not the best way, right? Because it's harder to know pre-ahead. So how they will work in each of the mini batch. So the better way is try to dynamically to adjust that. How to do that? It's very simple. So you can basically try to check the difference between two learned adjacent matrices in two consecutive steps. And if the difference becomes smaller and smaller, and once it is smaller some threshold, you can stop. So this is basically some results showing that how this iterative graph structured learning algorithm can work. So we can see that by working on the 7 different data sets, the first 4 is have the graph structure and also the initial node attribute. The last 3 is only have a graph know the attribute but don't have a graph structure available. So compared to the other method, seems like this method can work quite well. And so this is also some robustly to study because the graph structure, right? The one something that the initial graph structure have a noisy information. So therefore that basically is not stable, right? So the robustness will become a very important topic to understand here. So therefore so this graph structure learning become important because you can try to learn the graph structure based on the other information you have in order to make the system more robust. So therefore, that we want to study that you can definitely try to remove some edge or try to add some edge, try to add more noisy or to the original graph structure, and to see that how robust each method. And you can see that so this red color, right? The IDGO is always perform best according to different one. And this is kind of visualization result to see that so compared to the edit graph and the learning graph, indeed it's learned some very interesting structure compared to the initial graph. So we also have been, in chapter 9, we also talk about the graph classification, right? So we have discussed that before, right? So this is try to learn a graph level representation effectively so that we can perform a graph level related downstream task. And in the chapter 10, we talk about the link prediction. And in the chapter 11, we talk about one of the hottest topics today called graph generation. So this is very important, like in the drug discovery domain. And the graph transformation is another type of the new problem, the research frontiers, in a sense that so graph may have a different state, and so they may change the topology, but they belong to the same graph. So in that sense that so the graph transformation is just like English transformation, right? So you transform a language from one language to another language, but they're still stated for the same semantic meaning. So this graph transformation try to study this type of the new type of the method, new type of the problem in this domain. And so the dynamic graph neural is also very important because in reality, the graph is often evolve over time and over space. So how to develop an algorithm, try to adapt to this setting is very important. And the Hijira graph is also a very natural one, especially for the network embedding, right? So you have a different type of the graph node and also have a multiple relationship. So in that sense, so all the basic graph neural we haven't discussed before is not suitable. Okay, so in this chapter, so we particularly discussed so how to develop an effective, efficient algorithm for Hijira graph, and the AutoML graph. AutoML is all very important, right? This have been showing a very effectiveness for other graph, other neural network tuning, right? And so in the graph neural, so we also have so many different blocks. And how to automatically to learn a good combination of different settings, also a very interesting topic. And this one is contributed by the professor by Taylor, right? So thank you, Taylor, for this great contribution in the chapter 8. So we talk about this self-supervised learning algorithm. So this self-supervised algorithm have been well studied in the computer vision and the natural language processing domain. And in the graph neural domain, is also very important to leverage this type of the learning technique to improve the performance of the graph neurons. So final one, we'll talk about the application of the graph neurons. So how many time do I have?
So we have 15 minutes left, and then
okay. Let me quickly go through the application. Okay, and then I will give some time for the QA. So I will only talk about one application, the recommendation system. So because this is one of the hot topic today. So basically here, I'm just pick up one application for example called the session-based recommendation, or you can call the sequential recommendation. Okay, so this is a very important topic in industry and in the research committee as well. So basically, you have given an interactive sequence of the ongoing session, and you try to predict the set of items that the user may like to interact or purchase or to click. Okay, and the challenge here is how modeling this complex sequential dependency in this very short term time window. So most of the methods, they tend to ignore the historical sessions that have been presented, and this will be lead to the non-personalized recommendation. And also, even though some of the, some methods starting to using the user's historical session, they may ignore the other user's historical session. So you can see that. So once it started to modeling the dependency between different session user, it's naturally will have a graph, right? So that's why this so this is basically the basic math formulation for that. So this is basically, you can see that. So once you have this session data, right? This is first one is the user one. You have a click and like or buy different item, V5, V4, secondly, and this user in the second session they may interact with this V1, V2, V5, V3, right? And the user two in first session they may interact with V1, V4, V3. So you can see that if we put them whole together, you can create this as a global graph between each of the item and also the user. Okay, and therefore that later you can modeling this global interaction behavior, and then to generally modeling with this personalized session encoder, and therefore that you can create a better item embedding and user embedding, and therefore that you can make a better prediction. So this is basically the key idea. So when we, in reality, when we try to modeling, when we try to leverage the power of the graph analysis, the most important part, I think, is how to construct graph. Okay, this is very important, and that is basically give a thinking about how to construct graph, because you want to modeling the potential dependency between each of the graph node which have been previously missed, and if that information can be leveraged, then you definitely will give you definitely will learn a better representation for the original item. Okay, so basically this is just tell us how to build this general global graph, item graph and item user graph, and also the user graph. Okay, so this is basically give that. So once you have these heterogeneous graphs, how do you do the aggregation and try to generate the node embedding? And this is basically try to tell that. So once you have the information, right, then you have to consider how to generate a personalized session encoder. So then you have to consider current preference learning for each of the user, and also the general preference learning for each of the user. And therefore that you can generate the final personalized session representation for each session. And then finally you will use the loss to predict the next item probability, and then to optimize the objective function. And this is just some experiments showing that. So by considering the user's history information and also other user history information, you are able to generate a much better user embedding. Therefore, that you can generate a much better session embedding. Therefore, that you can do a more accurate prediction. So this is done for the recommendation part. For the computer vision part, it's a similar thing. Okay, for example, in computer vision, you can do this object detection, and then you can do this scene graph generation. You have this skeleton for each image. So all of them tell us that. So you can able to capture the dependency between the different objects, and therefore that you can create a graph between them. So last one showing that this is a video. Even in the video, over time, you will see the connection between the previous image frame and the next image frame. And therefore, they can also build a connection between them. Build a graph. In the natural language processing domain, this is one of the favorite topics I like. You can actually use a graph unit for that. The reason is very simple, because the human language is a high-level symbol. It's not just a simple sequence. Okay, you are able to generate so many different hidden structure, behind this text sequence. And this is just some example to showing that. So what kind of things that you can leverage, right? And then finally you can build a graph, and then you can using Graphene Units to generate a better result. And so this is things that we have been leveraged the Graphene Units for the program analysis. This is a similar thing, right? Because in human language is no much difference of the programming language, in terms of a computer, right? So therefore that you are able to find the dependency between different language token, and then to generate a graph, and then to do a better program analysis. And in today there are many countries that try to build a smart city. One of the important topics is how to do the urban intelligence. And we can see that, for example, this is the root network. You're trying to find the optimal path, right, from the original place A to the destination B. For Uber, Lyft, Didi, right, from China. So all try to leverage this type of the information, try to make a better design of the path. So this is definitely one of the important applications that Graphical can play important role here. So this is our last slides. So basically, this is a full picture of our Graphene Units book that we have 5 chapters in foundations and 9 chapters in the frontiers and 9 chapters in the applications. So that will help us that so people can really to better understand the global picture of the fast evolving research topic in the graphene surrounding the Graphene Units, and try to give them also detailed enough information about each of the research topic, and also how to use that in various other applications. And and also if you want to check out this our book, you can go to this website, and you will find all the information you need. And that's all. Thank you. Any question?
Yeah, I think those of you that want to kind of unmute or turn on our cameras, and thank our speaker. Yeah, that was really great. And if you have questions, feel free to jump in. Maybe we can start with the one that's put in the chat. Looks to be related to about over smoothing and over squashing.
Yeah. Yeah. So yeah, this is a great question. Yeah. So this problem have been discussed in the chapter 4, that's written by the Professor Jian Tang and also Professor Li. So over squash is a relative new topic. So they have been discussed a little bit, but I don't think they discuss a lot. Yeah. So as you can see, so that's the important thing and the limitation for the current Graphene Units book. That even that you write the book in 1 year, so you will see a lot of new topic rising, and so this is exact motivation why we want to edit a book like this Graphene Units book that try to present the most comprehensive topic, so that the people can use this as a kind of a starting point to quickly check all different kind of research topic, and then to find the one that you are really interested in.
Any other questions?
Hi, Dr. Lingfei. Thanks for your presentation. So I kind of have some questions related to the structured learning. So because for structured learning, definitely, I mean, that's the learning the age. So as long as we want to learning the age between multiple nodes, there involves like the powers to the 2, like number of the ages we want to learn. Then if the nodes, if the network size is a little bit large, how do we deal with this space complexity? Yeah, because initial graph is definitely maybe a sparse graph, but if we want to add some edges, there will be those all of the v to the power of 2 time space complexity. How do we deal with that? Thanks.
Yeah, this is a great question, right? So most of the graph structured learning paper, if you look at the data set, most of the data is very small. Yeah, that's because that's a complexity issue, right? The quadratic complexity in terms of graph and node. But in the IDGL paper, so we have been discussed an alternative way to do that. So we are able to reduce the complexity from the quadratic complexity to the linear complexity. So the idea that we briefly touch, okay, because that paper is not about that, but this is just a subsection. But I think this is an important research topic in the sense that you don't have to really compute the pairs of the a pairs of graph node in order to compute the similarity score. Think about this way. Okay, I don't know if you're familiar with the kernel or not. Okay, for example, originally, right, when we use SVM to develop kernel metrics, right? So there people have been developing many different approximation methods. You want to achieve the fast kernel approximation. One of the key idea is try to using no rank approximation. You want to approximate the inner product. So when we compute the similarity score between any of the pairs of graph node, essentially you try to compute kind of like inner product between two vectors. Okay. So therefore in order to achieve the acceleration, you can design some kind of like, you feel familiar with a nice draw method, or you feel familiar with a random feature method. So essentially you can design some random anchor node, and then you can compute the feature representation between the original graph node and also the anchor node. And then you can use that as a feature matrix. You can design the dimension of that. Okay, this is low rank dimension. And then you can compute the other one, the rank node with the other graph node, and you can use that low rank approximation to compute the inner product. And then you can compute the approximation to the original pair of the similarity score. I don't know if you get my point, but this is a very important trick.
Is it like instead of like node messaging passing, but we first like calculate the node and the anchor similarity, and use the node anchor similarity to recompute the node similarity? That's kind of.
You can think about as kind of like a triangle. Okay, now you want to compute the distance or similarity score between the node A and the node B. And now you want to compute that, you don't really have to exactly compute that. Think about, you can have a new graph node in, maybe some speakers or anchor node. I call it anchor node. Okay, you can call it C. Okay, and now you don't want to compute A and B because it's very expensive. Okay, now if we can have a way to cheaply compute the distance or similarity score between A and C and B, then you can use AC distance and CB distance to approximate the original AB, using the triangle equality equation to bound the arrow.
Yeah.
And if you sample many of them, you can use a Monte Carlo type of method to reduce the variance.
Okay, I think
and
that's
in that sense that you can greatly reduce computation.
Yeah, I think I got the general meaning. Also, it's
just take our paper. Yeah, I think in that paper, in our newspaper, we just briefly touch that point. But since I'm not really in the academia, so I don't have students working on that. But I think it's a very interesting topic. Yeah, so you can definitely move that away.
Okay. Yeah. Sometimes I'm thinking maybe like we can select some anchor nodes and do some message passing from like all the nodes to the anchor nodes instead of nodes to nodes.
That's a great idea. And remember how to generate this anchor node and how to prove that this anchor node will quickly approximate the original computation with some certain upper bound. I think it's definitely achievable and an interesting topic.
Thanks for pointing this out. I'm marked up in my mind. Yeah, thank you.
Okay, sure.
Any other questions?
There's another question in the chat.
Okay, so basically about the Graphene Units in anomaly detection. Oh, this is a great question. We have a dedicated chapter talk about how to do anomaly detection in Graphene Units. Yeah, so yeah, definitely encourage you to look at that chapter. I think it's chapter 25 or 26. Oh, 26, yes.
Another question just came in the chat about frameworks for doing large-scale analysis.
What do you mean large-scale analysis?
Hi. So just wanted to know, like, if one has large heterogeneous set of data set, how can one incorporate GNN analysis on these data sets? So suppose we have, say, from medical or healthcare, we have large data sets. And if we have to find some patterns for any kind of a disease or something along those lines, what are some of the available frameworks like the PyTorch or something along those lines, like Spark or those kind of libraries. Are there any such libraries for GNN?
So let me try to understand the question, okay? Because so you say some data set in the medical domain, right? So this data set is already in the graph data set, or is it's original data set, and you have to construct a graph on that.
Right. So this data set is not in a graph form.
Okay.
So
Okay.
I'm not potentially something like Neo4j or Yanis graph or something along those lines might be needed, correct? And then we need some kind of a Spark. So I was wondering if there was some libraries that supports understanding GNN.
So the two different parts, okay. So for example, I don't think there's a dedicated library that to tell you how to do the graph construction part. Okay, because graph construction typically is art. So we have a library called Graph for NLP. So this library, I can put that here. So Graph NLP, you can search that name. You can find in Google. You'll find the library. So this library is our attempt try to build a library for NLP community. Okay, because for NLP, your input is a sequence, and it's naturally represented in graph. How to do that? We have developed this methodology called the state graph and dynamic graph, and I believe this type of the learning philosophy is also suitable for any kind of other domain, for example, medical domain. So some of the function, maybe you are able to leverage the function we have developed there, okay, in order to build a graph for you. But again, so once you have a graph available, then if your graph is really large, right? For example, more than 10 million and even billion, in that sense that so you should, you cannot imagine a single computer node will do the job for you, because you may even simply run out of the memory. So therefore, we have a chapter talk about that. Is chapter 6. Okay, Graphene scalability. So people have been developed a bunch of the faster Graphene Units method. Essentially, it's approximation. Okay, sampling based method. Try to achieve that. I think along with this of the direction, DGL is a very good library, general library. And our library actually is Graphene NLP library is built on top of the DGL. Okay, so DGL you can use DGL for multi-threading and multi-node. So this will become important. But if we just not really familiar with Graphene Units to do the analysis, I would encourage you to first of all to use a small subset of the data set you have to starting to build some graph and then to do the analysis. Because once you have this experience, you are able to always using a bigger and bigger data set and to achieve a better result. But at the very beginning, it's very important to starting to build some graph along with your data set, and then to see some interesting results. And there are many libraries that can help you to do that.
Okay, all right, this is perfect. Thank you so much for the answer and
sure.
Suggesting a couple of libraries around this. Thank you.
Yeah, sure.
I think we'll have this as the last question that just came through in the chat.
Oh, okay. So on unsupervised learning. So there's two parts of a chapter talk about that. One in chapter 4, Graphene Units for node classification. So we have a subsection talk about variants of the unsupervised method in Graphene Units domain. And also, I believe in Tyler's book, chapter 18, self-supervised learning also introduce a bunch of the methods to do the unsupervised learning on Graphene Units. So you are definitely welcome to check out these chapters.
Well, thanks again. I think it was a really great presentation, great introduction to the book, and kind of pretty broad introduction to graph neural networks. So thanks again.
Yeah, thank you so much, yeah, for the invitation. I hope this book will be useful for students who are willing to learn this new topic, and for the researcher who want to find a new research topic. We have so many volunteers and foundations research topic here. Hopefully, you can find something interesting there.
Yeah, still waiting on my copy to arrive.
Okay. So if you have trouble to get a copy, let me know. I can ship my copy to you.
Yeah, I think the one Springer email just went to spam, and so then.
I see. Okay.
Thanks again.
Okay, thank you. Bye-bye, guys.
Have a good one. Thank you. Thank you, Tyler. As soon as it becomes available, I'll send it to be published on YouTube.
Okay, sounds good.
Cool. Talk to you later. Bye.